Chapter 23, Electric Potential. Electric potential covers electric potential energy U, electric potential V, electric field E, and electric potential V. Electric potential due to charges. Insulated conductor. You can find them in the timeline. Electric potential energy U. Electric potential energy U. We can infer that the electrostatic force is a conservative force. Thus, when that force acts between two or more charged particles within a system of particles, we can assign an electric potential energy U to the system. If the system changes its configuration from an initial state I to a different final state F, the electrostatic force does work W on the particles. Delta U equals UF minus UI equals minus W. Here, W is the work done by the electric force. Okay. This is a definition of potential energy, right? We only define delta U. And this work should be independent of path because it's a conservative force. For convenience, we usually take the reference configuration of a system of a charged particle to be that in which the particles are all infinitively separated from each other, and we usually set the corresponding reference potential energy to be zero. Suppose that several charged particles come together from initially infinite separations I to form a system of nearby particles, state F. Let the initial potential energy UI be zero, and let W infinity represent the work done by the electrostatic forces between the particles during the move in from infinity. The final potential U, delta U, equals minus W infinity. Here, infinitive means we set the U at the infinity is zero as a reference point. As is true of the other kinds of potential energy, electric potential energy is considered to be a type of mechanical energy. If only conservative forces act within a closed system, the mechanical energy of this system is conserved. We should use this fact extensively in the rest of this chapter. Electrons are continuously being knocked out of air molecules in the atmosphere by cosmic ray particles coming in from space. Once released, an electron experiences an electrostatic force F due to the electric field E that is produced in the atmosphere by charged particles already on Earth. Near Earth's surface, the electric field has the magnitude E, 150 Newton per coulomb, and is directed downward. Question: what is the change delta U in the electric potential energy of an released electron when the electrostatic force causes it to move vertically upward, so a distance d 520 meters? This is the electric field of Earth is towards the Earth. And this electron, it was absorbed a force by the E and move up. After move D, what is its potential energy change? We know F equal to W equal to F dot D. In this case, F equal to E. Okay, right. And this E, D is the same direction. Okay, this is E, this direction. Okay, these they are opposite direction. Okay, opposite, same line. opposite direction. So the angle is 180 degrees. So E dot D equal to ED cosine 180. And cosine 180 is minus 1. So W equal to minus, this is minus, two minus to get a positive, okay? Now, this is electric charge on electron, minus number. E is 150, D is 522, and cosine 180 is minus 1. 2 minus, we get a positive. Okay, we get a, okay. 1.2 times 10 to the minus 14 joule. And by definition, delta U equals minus W. So I put another minus, the potential change is minus 1.2 times 10 to the minus 14 electric potential V. The potential energy of a charged particle in an electric field depends on the magnitude of the charge. However, the potential energy per unit charge has a unique value at any point in an electric field. Notice the difference, okay? Divide by per unit charge. And we call it electric potential, not potential energy, okay? Thus, the potential energy per unit charge, which can be symbolized as U over Q, is independent of the charge Q of the particle we happen to use, and is characteristic only of the electric field we are investigating. Remember, V is a property of the field, electric field, nothing to do with which charge put on this point. For different charge on this point, they have different potential energy, but they have the same potential. The potential energy per unit charge at a point in an electric field is called the electric potential V, or simply the potential at that point. V equals Q over Q's definition. Okay. Note that electric potential is a scalar, not a vector. It's a scalar. Okay. The electric potential difference delta V between any 2 points I and F in an electric field is equal to the difference delta V equal to V final minus V, by definition equal to delta U over Q. And delta U is defined by minus W. So this is the definition of delta V. Delta V equal to minus W over Q. V final minus V initial equal delta V equal to delta U over Q equal to minus W over Q. If we set U infinity equal to 0, then V infinite initial equal to V infinity equal to U infinity equal to 0, because this is 0. Okay, so V initial is 0, V infinite is 0. Then we get V minus V0 equal to V equal to minus W infinity over Q. This infinity means is the work done starting from infinity, where W infinity is the work done by an electric field on a charged particle as that particle moves in from infinity to point 5. A potential V can be positive, negative, or 0, depending on the signs and the magnitude of Q and W infinite. This is definition. Okay? They can be 0, okay? Or positive or negative. The potential V at point near an isolated positive charge is positive. When a positive charge is established an electric field, and you move another positive charge from infinity to the final place, you have to, the work done by the electric field is negative, because outside force do the job. And then negative, you get a positive. So you have potential V a point near an isolated positive charge is positive. The metric system unit for potential is the joule per coulomb. 1 volt is 1 joule per coulomb. This is a volt equal to, this is energy joule, this is the charge coulomb. Okay. The electric field E is 1 Newton over coulomb, is 1 joule over coulomb. We know the Newton, okay, 1 Newton equal to the volt multiplied coulomb and charge Q, and 1 coulomb in the joule Newton per M. You put them together, we find 1 Newton over C is 1 volt of meter. That's the electric field E, unit volt over meter. 1 electron volt is the energy equal to the work required to move a single elementary charge E, such as that of the electron of proton. So a potential difference of exactly 1 volt. Okay, 1 electrovolt is the energy unit. It's not volt, it's energy, electrovolt. Okay, and electron volt is equal to 1.60 times 10 to the minus 19 coulomb. This one, multiply 1 joule of C, get 1.60 times 10 to the minus 19 joule. This is a relationship between them. Electric potential energy U is an energy of an uncharged object in an external electric field, or more precisely, an energy of the system consisting the object and the external electric field. It is measured in joules. Electric potential V is a property of an electric field, regardless of whether a charged object has been placed in that field. It is measured in joule per coulomb or volt. Work done by an applied force. Suppose we move a particle of charge Q from point I to point F in an electric field by applying a force to it. During the move, our applied force does work W applied on the charge, while the electric field does work W on it. They do at the same time. Okay? Now, suppose the particle is stationary before and after the move. That means delta K is 0, nothing changed. Okay? Then from the energy conservation, we know delta K equal to works applied force plus work by electric field. Okay? It should be 0. This is another definition, right? Okay, then we find work we do, work applied equal to minus work by electric field. Okay, and this one we know that by definition is minus delta U. This definition. Minus gets 2. So we find out the work we do, applied force, is equal to delta U. So you want to find the delta U, you just find the work done by us. Okay. And this work equal to Q by delta V. We are going to use this quite often. Okay. W equal to Q delta V. And then we know that W equal to minus Q delta V, because they are the same, right? So this is Q delta V, this must be minus delta V. Okay. And the work done by the applied forces equal to Q delta V. They have minus different. Okay. We can relate our works W applied to the electric potential difference delta V by the initial and the final points of the particle. Okay, so this gives us a lot of convenience. We don't have to consider what happened in the middle. only two terminals. Okay, two terminals. W applied can be positive, negative, or zero, depending on the signs and magnitudes of Q and delta V. It is the work we must do to move a particle of charge Q through a potential difference delta V with no change in particle's kinetic energy. Remember that the particle kinetic energy no change. If it change, then we have a new way to do it. Equipotential surface. Adjacent points that have the same electric potential form an equipotential surface, which can be either an imaginary surface or a real surface, physically surface. 1. No network W is done on a charged particle by an electric field when the particle moves between 2 points I and F on the same equipotential surface. You know this one? If they are both on equal potential surface, so delta V is 0, so V is 0, W is 0. 2. Equipotential surfaces are always perpendicular to electric field lines, and thus to E, which is always tangent to these lines. If E were not perpendicular to an equipotential surface, it would have a component lying along that surface. This component would then do works on the charged particle as it moved along the surface. But by equation delta V equal to minus W over Q, work cannot be done if the surface is truly as equipotential surface. This is 0, this must be 0. Okay. So the only possible conclusion is that E must be everywhere perpendicular to the surface, and E along the surface component is always 0. So, a family of equipotential surfaces, each surface corresponding to a different values of the potential, can be used to represent the electric field throughout a certain region. Now, this is 4 different value equipotential surfaces, and they can represent the electric field. Okay. A family of equipotential surfaces like this one, many. Now let's see the work done. So number 1 is the same line, the moving the same equipotential surface. Of course, W1 equal to V final minus V initial, they are same, equal to 0. Now look at the 2. This 2 is started from V3, go down to V4 and come back to V3. So the final point and initial point are all in the same equipotential surface. So delta V equal to 0. In this case, W2 is 0. Let's see W3. W3 is from V1 to V2. So the delta V are not equal to 0. So W3 are not equal to 0. And W4 is from 1 to 3 to 2. The final point is the same thing as this one. The delta V the same as the previous case. So W4 equal to W3. Okay? Okay. This is some electric potential, equipotential surface, okay, line of surface to the electric field line. They are perpendicular. This is electric field line or the positive charge, and this sphere actually is the equipotential surface. Okay, this is a different situation. This is an electric dipole. Okay, this is a parallel charge. This tutorial we are going to study next detail. Now we know that when her hair is E along, extend along electric field. Electric field E and electric potential V. calculating the potential from the field. Now, this is electric field. We have initial point here, and the particle move to F by some force. Okay, this is for force. Okay. Now W equal to F dot ds integration. That's the basic mechanics. And here F equal to electric force. Okay, so this is equal to Q0E. This point has a charge Q0. This is E exerted on it. Okay, that point. Okay. And see, that's one with the integration from initial point to the final point. And Q0 is constant taken out. So this is E dot ds integration. And with from the electric potential energy point of view, a W equal to minus Q0 delta V. Delta V is V final minus V initial. They are the same work done. We just calculate or by definition by different point of view. They must be equal. In this way, we just find compare this and this. We get V final minus V initial equal to minus integration E dot ds from I to final. This is calculating the potential from the field. Integration plus minus. This is what I try to remember. This should be independent of the past because electric force is a conservative force. Or we set Vi equal to 0. That's why we have at infinity. Okay, infinity. And then we have this infinity. This is V. The point at V equal to minus E dot ds from infinity to this final point position. Okay. And then this means integration plus minus this relation, calculation the potential from the field, integration plus minus. Example. Figure A shows 2 points, I and final, in a uniform electric field. There's electric field going down. Okay. The points lie on the same electric field line, that's the point line, this one, initial point to the final point, in the same line of E. Okay. And are separated by a distance D, and this is distance D. Okay. Okay. Find the potential difference V final minus Vi by moving a positive test charge Q0 from I to final along the path shoot, okay, which is parallel to the field. Now, by definition, V final minus V initial equal to minus integration from I to final. Here the E is a uniform E. ds is along the direction of the E. So E dot ds equal to EDS. Right? EDS. EDS equal to EDS cosine. They are the same direction, cosine 0. Okay? Cosine 0 is 1. Okay? And E is uniform. So we take this E out. Okay? We can take this E out. And the integration distance equal to S. This total S is D. So this is equal to minus ED. Okay. Question B. Now find the potential difference V final minus V initial. By moving the positive test charge Q0 from I to F along the path ICF shown in the figure. Instead, we go from here to here. It goes from here to here. Okay. We say it should be the same because the electric force is a conservative force. The work done by it should not depend on the path. Okay? Then we prove it. Okay? So V final minus equal to integration. This integration is, we can divide it to 2 parts. First is I to C, and then C to final. You have a final in front. Okay? Then we do it separately. Okay? In this section, E downward, S horizontal. So your angle is 90 degrees. Cosine 90 degrees is 0. This is 0. The second one, E is this direction. ds, they have an angle 45 degree. Okay, 45 degree. So this one equal to minus cosine 45 ds from C to F. Okay? E is constant anywhere. Cosine 45 is square 2 over 2. Okay? So this one, okay, that is E square 2 over 2 is this one. Okay? Integration ds. This is length S. In this case, is this one. This one. And this one is d squared 2. D squared 2. So we get minus dE. The same as before. Now reverse. Calculating the field from the potential. Now we look at this. A charge Q0 is moving in an electric field. Okay. This is a two differential surface like that. This is location. This is E. Okay. Between angle at any point you have a theta, which is angle between ds and E. Okay? And we see the dW when you move, you have the work done is minus Q0 delta V dV. The dW is what? Is equal to F dot ds. In this case, F equal to Q in E, this direction. ds direction. Okay, and this one you extend it equal to E cosine theta. The cosine theta can change. Okay, any direction. You don't know. Okay, and so we find out. Okay, we compare these two. We find that E cosine theta equal to Q0 cancel is minus dV over ds. We round it called minus rho v rho s. Okay, and E cosine theta, what is it? Is the component of E in the direction of ds. Yeah. So this equation become E around direction s equal rho v rho s. This is what we get. We get a different s, we get different derivative. The component of E in any direction is the negative of the rate of change of the electric potential with distance in that direction. So Ex equal to minus rho v rho x. Ey equal to minus rho v rho y. Ez minus rho v rho z. And we have three components. We got E. The E equal to Ex rho v rho x I plus Ey. Ey is minus rho v rho y j plus Ez minus rho v rho z k. This is the E. Okay, we find it. Okay, and this one by mathematics is minus gradient A x y z by definition. Okay. The simple situation where the electron field E is uniform, equation becomes Es equal to delta S over delta V over delta S. We can change this one. Electric potential due to charges. Potential due to a point charge. This is a point charge Q. It produces electric field around it. We want to find the potential at point P with distance R. Okay, this big R. What we do, we see that's what we should give it answer. V equal to 1 over 4 pi epsilon 0 Q over R. This is the answer. We will find it. We just learned the delta V equal to minus E dot ds integration. Now, we move this one from point P, distance R, to infinity. See what's happening? Now, we use this formula. Initial is V here, distance R. Final is infinitive. So infinitive V is 0. Okay. So we put inside the E dot ds. ds is along R, so dr. Okay. And we do it is from big R to infinity. Okay. This is what we do. Okay. And E dot dr, with the E is along the dr direction. So E dot dr is EdR. Okay. And we put this E inside. E, we know that one by Coulomb's law. 1 over 4 pi epsilon q over r squared dr. Integration from r to infinity. This integration is very easy. It's minus r, 1 over r. So it's a piece of cake for you, right? So we finally we get the answer. V equal to 1 over 4 pi 0 q over r. Or we change this r to any point. This is the equation. Okay, this equation. This is the potential produced by point charge q. The potential V at any point around a positive point charge is positive. Now, this is positive, so this is positive. Okay. Relative to zero potential at infinity. This is defined. Okay, define V equal to 0 at infinity, then you have this equation. Okay. This is when r equal to 0, it's infinite. Okay. The potential V at point around a negative point charge is negative relative to the zero potential at infinity. So also we set the infinity potential is 0. And then this Q is minus. That means a charge around a minus charge Q, the V is negative. Any point for that is negative. This point is belong to the field produced by the point charge. Equation also gives the electric potential outside or on the external surface of a spherical symmetric charge distribution. A sphere, we can look at it as a point. If you calculate the V outside, we can treat it as a point charge. Potential due to a group of point charge. With the help of the superposition principle, V equal to sigma Vi, the sum of the potential produced by each point. The I is from 1 to n. And we know each one is 1 over 4 pi epsilon q I over ri. We have a sigma I, different q, different digits to our point. Here, Qi is the value of the nth charge. This one. Ri is the radical distance of the given point from the i's charge. And V is a scalar, and E is a vector. They're different. Sample. What is the electric potential at point P, located at the center of the square, at point charge shown in the figure? The distance D is 1.3 meter, and that of the charges are Q1 12 nanocoulomb, Q2 minus 24 nanocoulomb, Q3 plus 31 nanocoulomb, Q4 plus 17 nanocoulomb. Okay. Well, this is very simple question. Okay. V equal to sigma Vi. We put everything inside. We have a common factor 1 over 4 pi epsilon taken out because Q1 over R. The distances are the same. The 4 charges distance to the P is the same. Okay, what is this R equal to? This R equal to half this one. This one is square root 2D. Okay, so we put this number inside. This is R is D over square 2. We get the answer, 350 volt. Look, this V is different. This V. This is electric potential, and this is a volt, a unit. In this case, we can find it. Okay, the equipotential surface when surface V equal to 350, like this one. This point is on this one. Sample. Question A. In the figure, at 12 electrons of charge minus E are equally spaced and fixed around the circle of radius R, relative to V equal to 0 or infinity. Okay. What are the electron potential and electric field at the center of the circle due to these electrons? We found this potential V and electric field E. Now we see very simple. This is a sigma. Okay, put together 12, and this one equal to this electron minus Q over 4 pi epsilon over R. This one, we get the answer. Okay. And E, look at this 12, they arranged symmetrically. So this one and this one put together is 0 because they are in the same line. This one and this one put E is 0. So the final E is 0 by symmetry. Question B. If the electrons are moved along the circle until they are non-uniformly spaced over a 120-degree arc. Now, this arc is 120 degree. This space arranged randomly. What then is the potential at C? How does the electric field at C change, if at all? We still do the same thing. So the V is still the same because this is a scalar. We just put them together. We get the same answer. And E are different. In this case, E is not equal to 0. We have to calculate it based on the detail. So the V does not change, the E changes. Potential due to an electrodipole. This is the electrodipole, we know that, okay? It's the same magnitude, different sign, positive Q, negative Q, okay? And we see the potential should be sigma, okay? And they have different distance to this one. So we put this formula, this is equal to 1 over 4 pi epsilon, positive Q plus R plus. This is minus Q over R negative. This Q the same. We rearrange it, we get it that equal to 1 over R positive plus a minus 1 over R minus. And this can rewrite as R minus minus R positive, R minus dot R positive. Now we see this I minus, this I positive. This is distance is R minus minus R positive. This is the one. Okay, and we look at this one. This one is this one. This one actually equal to D cosine theta. This is this one, D cosine theta. So we put the one D cosine theta, and we look at R minus times R positive. They equal to R squared. This is R squared. Okay, this is R plus half D cosine theta. This is R minus, we multiply by them together, we get R squared by the D cosine square theta. And it is approximately equal to R squared. So we put this one inside, we get the Q, this is D cosine theta, this is R squared. R is the distance, this point to the center of the electric dipole. Okay? Yeah. And we write P equal to QD. This is a dipole. Okay? Now QD is dipole. So rewrite this one. V is P cosine theta of R cubed. Induced dipole moment. Many molecules, such as water, have permanent electric dipole moments. In other molecules, nonpolar molecules, and in every atom, the centers of the positive and the negative charges coincide, and thus no dipole moment is set up. This is no dipole moment. Okay. before the electric field applied. We call it permanent electric dipole is zero in this case. But water, they have it. They have electric dipole moment. Now when we applied E, and we saw the electron will move around the atoms, move in opposite direction. And then we can see it is positive move along the E direction. Okay, this is the P. P is from negative to positive. We have this P. Okay, dipole. Okay. However, if we place an atom on a non-polar molecule in an external electric field, the field distorts the electron orbits and separates the centers of the positive and the negative charge. Because the electrons are negatively charged, they tend to be shifted in a direction opposite the field. This shift set up a dipole moment P that's point in the direction of the field. This dipole moment is said to be induced by the field, and the atom or molecule is then said to be polarized by the field. It has a positive side and a negative side. When the field is removed, the induced dipole moment and the polarization disappear. Potential due to a continued charge distribution. We know the dq produces dV, like this equation, like the point charge. And we divided a continued charge body as many composed dq continuous distribution. And then we see the V equal to integration, sigma df, this is integration, okay, and include this integration. Whole volume. Okay? So we find V equal to 1 over 4 pi integration dq over R. This is potential due to a continued charge distribution. The integration must be taken over the entire charge distribution. Then we do the detail. Line of charge. This line is continued distribution of charge. So what we do, we divide this line into many dq. Like this one. We take a reference X, orange is here. This very dq location at X. This is the P, I want to find the potential. Okay. This is D, the distance. I take this locating at X with dx as a representative of all section dq. How? When X equal to 0, this is a very tiny dq, this particular case. When X equal to L, at this point, it represents a very tiny dq at this equation. When X changes from 0 to L, it represents different small section dq. Okay? Now, we find representative to do the calculation, and then we extend it by integration. dV, this one, produce dV at point P is equal to this one. Now we see the R. The R is equal to d squared plus x squared square root. So the V equal to total integration, sigma dV, total integration, okay? We'll put this one inside, okay? dq, this dq is charges lambda dx. Lambda is linear density, the charge per unit length. And now we have dx, so multiply is the dq. And that's R, we know that this R equal to d squared plus x squared square root. Different x has different R. Okay? And we do the integration from where to where, from x equal to 0 to x equal to L. That's it. Okay? This is a electric potential produced by line of charge. In this case, the P is perpendicular to the line at M. This integration is the easier one. Okay, we do the integration from 0 to L. We can get the answer. We put the 0 to L, we get the final answer. I don't remember this one. Then I know how to do it. Okay. Second, a charge disk. This is disk, okay, a lot of DQ. So what we do, we look at this, divide this disk into many charge ring. This is ring. This ring is radius R prime. We find this one, okay. You know what? The distance of element on this charge ring, the distance to P are the same, is R. This R equal to R prime square plus Z square, the location of P, square root, right? So because V is a scalar, so we can put them together by symmetry reason. So the dV produced by this ring is dQ of V. We write it down, okay? Write it down. What is it down? What is dQ? dQ is total ring. The total ring is 2 pi r prime multiply dr prime, is area, multiplied by charge density sigma. 2 pi r prime, dr prime, the area of this brown color, multiply the charge density on surface, sigma. This is dq. This r equal to r prime square times z square, square root. This I prime is a variable. R prime changes from 0 to big R. Then it covers everything on this charged disk. So this R prime is integration from 0 to big R. We done? Then we do the detail. This is very simple detail. 2R prime dr prime equal to R prime dr prime square. It's a very simple one. So we get this extra R. This is very simple integration. Finally, I get an answer. Okay, get an answer. Sample. The electric potential at any point on the central axis of a uniformly charged disk is given by equation. We just learned this one. Okay. Starting with this expression, derive an expression for the electric field at any point on the axis of the disk. Remember the relationship between V and E? Yes. E along this direction, Z direction, is minus rho V rho Z. Okay? Let me see. Derivative plus minus. And we have V, we do the derivative respect to Z. And we put the minus, we get a Z. So we take this constant out. This one rho Z, okay? This is rho Z. And then we finally, this is 1, get this answer. We get this answer. This one minus, so we turn it wrong, become this one. This one we got to use it, okay? If Z equal to 0, it means this point at the center of the disk. This is 0. The E equal to sigma over 2 epsilon 0. We will use it later, okay? This is conductor. Okay? Not a conductor, it's a charge disk. Electric potential energy U of a system of point charges. We define the electric potential energy U of a system of point charges held in fixed position by forces not specified as follows. The electric potential energy U of a system of fixed point charges is equal to the work that must be done by an external agent to assemble the system, bring each charge in from an infinite distance. This is the definition. This definition is important. How we handle it. We bring every point from infinite to this point, see how much work the electric force had to do. That is the potential energy U. Now, 2 points. 2 charges had a fixed distance R. What is the electric potential energy of the configurations? Now we do that. We mentally build up the system, starting with both charges infinitely, far away and at rest. And then we bring Q1 from infinity and put it in place. We do no work because no electrostatic force acting on Q1. But when we next bring Q2 in from the infinity and put in place, we must do work because Q1 exerts an electrostatic force on Q2 during the movement, right? Okay. So then, by definition, the system of potential energy, okay, equal to the work done by me. Okay, the work done by me, not by electric field, by me, definition. And this is equal to Q2V. Q2V. And V, we just know this one is Q1. This is the one produce electric field, Q1 over R. So, we know the 2-point charge, they have electric potential energy, is this one. If the charges have the same sign, we have to do positive work to push them together against a mutual repulsion. Hence, the potential energy of the system is then positive because I do work for them. Whereas energy, they have it. So what they have at potential is positive. If the charges have opposite direction, this is a minus number, as we have to do negative work against their mutual attraction to bring them together so that they are stationary. The potential energy of the system is then negative. Sample. Figure shows 3-point charges held in fixed position by forces that are not known. What is the electric potential energy U of the system of charges? Assume D is 12 centimeter, and that Q1 equal to Q. Q2 is minus 4Q, and Q3 is positive 2Q, in which Q equals 150 nanocoulomb. Now, by definition, we see the whole potential energy equal to U12 plus U13 plus U23. And each one, we have learned this one, is 1 over 4 pi Q, Q1, Q2 over D, distance D, plus Q1, Q3 over distance D, plus Q2, Q3 over distance D. That's it. Okay, we put them together, we get the answer. Okay, this is 17 million joule minus. Sample. An alpha particle, 2 protons, 2 neutrons, moves into a stationary goal, 79 protons, 118 neutrons, passing through the electron region that surrounds the gold nucleus like a shell and headed direct towards the nuclei. Electrons are outside. The alpha particle slows because they are positive. Okay. Until it momentarily stops when its center is at radius distance r 9.23 femtometer from the nuclear center. When r equal to this distance, they stop because they repel with each other. Okay. Then it's moving back along the incoming path, moving back. Because the gold nuclei is much more massive than the alpha particles, we can assume the gold nuclei does not move. What was the kinetic energy Ki of the alpha particle when it was initially far away, hence external to the golden atom? Assume that the only force acting between the alpha particle and the golden nucleus is the electrostatic Coulomb's law. Well, look at this. We used energy conservation, mechanical energy conservation. Ki plus K I equal to K final of U final. Okay, the final is away, final away. Okay, we know this one. Ki K final is infinity. This is 0. And finally, they stopped here. The K final is 0. And then we will find Ki. Ki equal to U final. What is U final? U final is two particle, 1 over 4 pi epsilon Q1, Q2 of R. R is distances. Okay, distance is given. Q1, Q2 given. So Ki, I know that's what. Q1 is 2E, 2 proton, 2 strong, 2E. This is a 79E. Okay. Distance is given. Okay, so we get a Ki. This Ki equal to half mVi squared. Okay, isolated conductor. Potential of a charged isolated conductor. E inside is 0. We have explained before. If it is not 0, we will see the current inside, and it's not true. And E surface is perpendicular to the equipotential surface of the body, conductor. Okay, so it's perpendicular to the surface, equipotential surface. V inside is a constant. Okay. Why? Let's see. V final minus V initial equal to minus E dot ds. This E inside is 0. I is 0. So this is 0. That means V final equal to Vi anywhere is constant. Then we put an excess charge placed on the isolated conductor, and it will distribute itself on the surface of that conductor so that all points of the conductor, whether on the surface or inside, come to the same potential. This is true regardless of whether the conductor has an internal cavity. A plot of V both inside and outside of a charged sphere records share of radius 1.0 meter. This is this is the border. Inside, V is constant, not necessarily 0. And outside, we treat this as a sphere at point. The V goes as well, like 1 over 4 pi to 0 Q over R. Right? Yeah. V outside equal to Q of 5 over R. B. A plot of E for the same share. Inside, E is 0. And outside, we treat it as a ball, so that V equal to Q over 4 pi R, R squared. This is a vector, this is a scalar. This is an isolated conductor in the external field. E inside is 0. E surface is perpendicular to the surface. Look at this. Okay. And the magnitude equal to sigma over epsilon 0. Sigma is the charge density. A different place is different. It's not uniform. An uncharged conductor is suspended in the external electronic field. The free electrons in the conductor distribute themselves on the surface so that to reduce the net electric field inside the conductor to 0 and make the net field at the surface perpendicular to the surface, because the electron, they redistribute it. This is a very interesting experiment. The largest spark jumps, high pressure, jump to car body, and then they go from the tire to the ground. Okay. And so, leaving the person inside unharmed. This is very important. Right? An isolated conductor has the following properties. 1, equal potential. V is constant. 2, charges on outer space, not inside. 3, except spherical conductors, the surface charge does not distribute itself uniformly. It's not uniform. 4, E inside equal to 0. E surface equal to sigma of epsilon 0, perpendicular surface. Charges are redistributed in an external electric field so that E inside is 0. Next chapter, chapter 24, capacitance. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.